In the last few segments, we've been focusing on an algorithm design paradigm called dynamic programming. Recall that the idea of dynamic programming is to ask a top-level question for which we don't know which answer will lead to the optimum solution, but we try all possible answers. And then we recurse on the resulting sub-problems, and ultimately we figure out what was the right answer to the top-level question, and therefore what was the optimum solution. So that's dynamic programming. Sometimes problems have a structure that allows you to ask a top-level question and then know the best answer immediately. If that's the case, then you can make your top-level decision right there and then recurse on the resulting sub-problems. But still the general idea remains to take an overall problem and nibble away at it by answering the top-level question and creating a smaller sub-problem in this way. So when you can answer the top-level question immediately, make the best choice for the answer to that question right away, we have what's called a greedy algorithm. An algorithm is called greedy because it's deciding to make the best decision at the moment without regard to the long-term consequence. It's not worrying about the overall optimum, it's just choosing what looks best in answer to the question it's asking right now. And it turns out that for certain problems, greedy algorithms actually will produce the optimum answer. Because in a greedy algorithm you're answering the top-level question right away, the algorithm itself is often quite simple compared to dynamic programming, which can lead to somewhat more complicated algorithms, as you saw last time. But proving that a greedy algorithm is in fact producing the optimum answer turns out to be harder than for dynamic programming. So the trade-off is you design a more efficient algorithm and a simpler algorithm, but proving that it's correct takes a bit of work. When you can do it, of course, you should use a greedy algorithm rather than a dynamic programming algorithm. All right. So with that background, let's actually look at an example of a greedy algorithm. Okay, so I've told you what greedy algorithms are in general. And I said, as before, the slide also says that greedy algorithms are easy to design but hard to prove correct. So here is the very simple example of a greedy algorithm. You're given n jobs j1, j2 up to jn to perform, and you're given a deadline t for how long you have a computer available to you. So you got to do whatever jobs you can within the time window of length t. We also know that job ji takes ti units of time to complete. So let's say that these are all integers. T is a very big integer. That's the amount of time you have the computer for. And so each of these jobs is a computational job. Ji takes ti units of time on the computer. And of course, the computer can only do one job at a time. And you want to find a way to maximize the number of jobs you can do within the time that you have available, within time t. So all you care about is how many jobs can I get done within time t? All jobs are equal. The more jobs you can do, the better for you. So what should you do? So which job should be done first? That's the top-level question. If we were doing dynamic programming, we would have said, I don't know the answer. Let me try every possibility for which job to do first. But because this is going to be a greedy solution, and actually we will be able to answer this question right away. What we will say is, we should do the job that takes the smallest amount of time first. Why does that make sense? Because it leaves available the maximum amount of remaining time to perform the other n-1 jobs. And you acquire a reward of 1 for doing one job. So the answer to this problem is really, really simple. You just sort the jobs in increasing order of the times they take. So the shortest jobs are first and the longest jobs are last. Okay. Complete as many jobs as possible in this order until t units of time have passed. So the claim is that this is the best you can do. Why is that? It should be obvious to you that you couldn't do more jobs than what we are doing by this algorithm, but let's see if we can come up with a little bit of a justification. Supposing the first job that you do is not the shortest, but something else. Well, if you're going to do the shortest later on, you can move the shortest to the first place, and that wouldn't change anything. So maybe is there a better solution that involves not doing the shortest job at all? Well, there cannot be, because you could always replace the first job by the shortest job, and then you would still have as much time for the remaining jobs in your solution. So even if your solution does not contain the first job, you could replace whatever job it is doing first by the shortest job, and it would still be another solution of equally good value, the value being the number of jobs you do. So it's clear that doing the shortest job first is a pretty good strategy, and that is the greedy algorithm. And you can see this algorithm is really fast. All you have to do is sort n jobs, that takes n log n time, and then keep performing jobs from shortest to longest until your time t is up. That's only a linear process. So the overall running time of this algorithm is order n log n.